And today, Andreu will continue with part 2 of his talk. So
Yep.
the Zoom meeting is yours.
Okay, thank you. All right, so let's just recap a little bit what we did last time and where we're going next. So, okay, first of all, our goal is to show an old theorem of Fürst-American-Weiss, but with the new methods that come from the work of Prandtl and Pelouse that have been transferred by Frantsikinakis to the ergodic theory world, right? So let's recall what the theorem said. Fürst-American-Weiss theorem says that if we look at the averages of TNF, TN squared, TN F1, TN squared F2, then if either of the FIs is orthogonal to the rational Kronecker factor, then the averages converge to 0 in the L2 sense. Okay, so this is what we want to show. Now, Fürst-Weiss proved this in a different way from what we're going to do now. But what we're going to do kind of relies on seminorm analysis and just reducing the step of the seminorm. Okay, so what we did last time was, okay, first, so this is just a sketch that is not good enough. So this is the rigorous proof, right? So what we did first was, okay, if we don't converge to 0, then I can assume that this F2 here has a special form. Namely, it's a Wick limit of something that looks like this. So the GKs are bounded by L infinity. And here, sorry, this should be F1 bar, by the way. And the T minus N squared simply comes from precomposing with Tn squared here. So it makes a lot of sense that something like that shows up. And as we saw, this special form of the F2 is just achieved by working with contradiction, right? If we don't converge to 0, then something must happen. And just analyzing that kind of, not immediately, but after some analysis gives us that F2 can be taken to have this special form. Okay, that was the first step. Then, where am I? Here. Then, so this is not a step that we really worked on. It's kind of something that we take for granted because of the familiarity with this fact for most people here, which is that for polynomial averages, they're controlled by seminorms. Namely, if a seminorm is 0, then the whole average is converged to 0. So the way we're going to use this is we're going to say, okay, so if we don't converge to 0, then necessarily this F2 has to have large average. Okay, and more particularly, we're going to use this not with this just F2, but with the F2 tilde that we constructed in step 1. Okay, and more interestingly, what we're going to do, so the next two steps are, okay, so if the F2 tilde has positive 3 seminorm, then we can say something about how it correlates to eigenfunctions. And then because of that, we're going to be able to say that actually the 2 seminorm is positive. Namely, F2 has non-trivial projection onto the Kronecker. That's kind of what we're going to get out of it. Okay, so this step is actually not even really hard. This is just, it just follows from an application or two of the Van der Korpe trick and just a definition of, well, not just a definition, but the fact that seminorms are characteristic for linear averages of the form AN, BN, CN. Okay, this is kind of a standard fact. Okay, so what we're going to do today is first show that, remember, for not the F2, but the F2 tilde, which has this specific form in terms of an average that depends on both K and N, like that. Then we want to deduce some positivity properties of correlation with the eigenfunctions. So here's some notation that we'll need. We say that this E of t is the set of functions that have absolute value 1, so almost everywhere, and our eigenfunctions. So Tf is equal to E of t f, where E of t here, remember, is the notation that means e to the 2 pi I t. Okay. And something that I introduced last time, I'm going to keep using, is this delta operator. All it does is, if you have an f, it gives you Tnf times f bar. Okay. Now, the proposition that we're going to use next, this is the main part of step 3, is just proving this proposition. So basically what we're going to do is, for ease of notation, we're going to abstractify the way F2 tilde looks like. And we can say it looks like a limit of averages of F and K. Notice that there's a dependence on both N and K. We can also assume, without loss of generality, the way we constructed it, that they are all bounded by 1 in the L infinity norm. So that's all without loss of generality. And now what we want to say is, okay, so remember, right? Like, even though we're saying all this quite abstractly, we're thinking of applying this to steps 1 and 2 combined, right? So we want to say, okay, if this seminorm of F is positive, then I wanted to do something, and some correlation with eigenfunctions. And what this is more particularly is these two claims here, namely, there exists a set of positive lower density, capital lambda. There exists an eigenfunction, chi n1, such that this correlation is positive. So this just means take real part, and the function delta n1f correlates with the character or eigenfunction chi n1. Okay. And also this other more complicated property here that has a lim inf and a lim sup and a bunch of averages. So if you recall from the strategy of the proof, there was a point where I said, if we could commute the expectation and the delta operator, then we would be done, kind of. So this is the more rigorous way of doing that, really. So what it involves is actually creating a new variable here for the delta operator. And then instead of just chi n1, we involve chi n1 and chi n1 prime bar. Okay. But this, actually, as we will see, this just pops out of the proof naturally. So how do we show this? We just use the definition, namely, first, by the definition of the seminorms, the 3 seminorm to the 8th power of F can be realized as the averages of the seminorms of delta n1f. But now, instead of the 3rd seminorm, is the 2nd seminorm. And by assumption, this number was positive, so this limit is positive. And now, so here are a couple of things that we have to use. When analyzing the 2 seminorm of a function, it's the same as if we analyze the 2 seminorm of the projection of this function, namely this delta n1f, into the full Kronecker factor. Okay. And now, because the Kronecker factor is spanned by eigenfunctions, and the definition of the 2 seminorm. So this you have to have worked a little bit with the seminorms to show that the 2 seminorm of a function is exactly correlated with the L4 norm of that function when you take it on the rational Kronecker. And the reason is because if you start computing the averages f, tn1f, tn2f, tn plus n1 plus n2f, and you apply this to eigenfunctions, you see that a lot of things just cancel. This is some computation that I'm going to omit. And what you get is just the sum of the coefficients to the 4th power. So in particular, what this means for us is, if this guy is positive, then necessarily, because of the averages, right, there exists a character that they all correlate to. So this whole thing here, so this implies, this positivity implies that the averages of the delta n1f correlate with some eigenfunction. Okay? Because if they were all 0, then you would be able to deduce that the 2 seminorm is 0. So in other words, if you have large 2 seminorm, then you must correlate to an eigenfunction, because L2 is spanned by eigenfunction. Okay. Now, because this is a lim inf, I can just take the n's that are good for me. In particular, I take a subset of integers that has positive lower density, such that this thing is true for a particular a bigger than 0, just by definition. And now all I have to do is just expand the definition of f. Remember that f was given by these averages here as a weak limit, right? So now if I do that, and I apply Cauchy-Schwarz once, so I'm not really going to say much about these steps. I mean, if you want to track the steps carefully, this is so it's not absolutely trivial, but it's not too bad. So what you get from this, and just expanding what the f is this Cauchy-Schwarz, this inequality here. And then just expand what this square means, and you get exactly, by subadditivity of the lim subs, you get exactly this. You kind of already see it here on this step. Okay. So this was just a technical step that tells us something like, well, if your averages of the two semi-norm are positive, then you have some good correlation with eigenfunctions without taking the averages, or at least moving the averages outside. And now comes the most important step, in my opinion, which is what allows us to lower the semi-norm number. Namely, we go from the 3 semi-norm to the 2 semi-norm. And that's the second to last step. And with that, we'll be able to just show what we want. So, okay. So what we want to do is focus our attention on F2 tilde, right? So we said that, well, if we don't converge to 0, we might as well assume that for an F2 tilde of the form that we described before, right? Which has some averages and some GKs, namely like this, right? We have 3 semi-norm positive. So now what we'll do is show that, in fact, the 2 semi-norm is positive. And this, right? So this part of the proof is quite hard, and I'll just try to give the main ideas here. Now, okay, so first of all, because of what we did just now, if this F2 tilde has positive 3 semi-norm, we know something about correlations to eigenfunctions and some averages, right? Namely, we know that for some set of positive density, there exists and some eigenfunction of the system, we have both this inequality and this other inequality here that's I couldn't even fit in one line, right? Because now I'm applying it to a complicated function. Okay, so this really, I'm not doing anything. I'm just applying proposition 3 to this particular function F2. So my f and k's are these t minus n squared gk, etc. Now, the next step that is really hard is we want to say, we want to be able to forget about this 12, but in a particular way. We want to be able to say that the chi-n1s here don't depend on n1, but only on capital N for when we're taking the averages, right? So this is going to take most of the proof. And okay, so first of all, the chi-n1s are just eigenfunctions, so we can write this. And so if we look at, wait a second. Right, so we precompose with t minus n squared here, and then we just use the fact that, so then a tn squared will pop up here, and thus, if we use the Cauchy-Schwarz inequality to get rid of the GKs, all that we're left with is the tn applied to this function. So if we use Cauchy-Schwarz, it's the same, 12 implies that we have these averages of L2 norms being positive. Now we're kind of in good shape already, if you remember, for using the spectral theorem, which was part of the sketch of the proof, right? We have just a bunch of complex numbers and Tn of some function. So we're going to use the spectral theorem together with the 2 lemma to get a bunch of positive measures with total mass less than or equal to 1, and a bunch of L2 functions, in fact, L infinity, right? Given by this lim sup here, such that this lim inf is bigger than 0. So all I'm doing really is, this guy is just becoming the e to the nt, right? Because this has an arbitrary, this is still a function in L2. Okay. So by the spectral theorem, all I'm doing is I'm transforming the problem of showing that the chi-n1s don't depend on n to something on the torus, right? So, okay, so what do we have? We have that this guy is positive, so there exists some a prime and n1 comma n prime between 1 and n, such that these L2 norms are positive. Okay. Now, after that, we can find a subset of positive lower density, such that for any little n1, now notice that here we're forgetting about the second variable and having it only depend on capital N. That's part of the step that we're trying to do. And so because these averages are bigger than A prime, we can have it without averages, right? So we find a subset of positive density. And now if the L2 norms are bigger than A prime, by the pigeonhole principle, there must be some numbers, right? Just in the 0-1 interval for which we have it. This inequality bigger than A prime. And now finally, we are able to say something about the alpha n ones, namely this. So now here comes another step that's important, that's omitted, and is that, remember that at some point I said, well, when we look at the averages of the form nt plus n squared alpha, it wasn't as complicated as this, but it was of the form nt plus n squared alpha. I said, well, as long as t does not come from a finite set of the torus, then we have convergence to 0, actually. So that's what allows us to say that we were not going to have dependence on. So sorry, that the chi n ones only depend on capital N, because now we're going to be able to say something about the eigenvalues, namely that they're all controlled by this alpha n1 prime comma capital N that only depends on capital N. So this average of exponential function, this exponential sum being positive can only happen if this difference is in a finite subset of integers. And now this is the key that allows us to say that the chi n ones only depend on capital N. So we find a further subset of positive lower density so that our eigenvalues are only determined by capital N. And that's why I'm going to call them beta subcapital N, right? So it's something that comes from this finite subset of Q plus the alpha n1 primes, taking this mod 1, of course. And now with this, we're ready to show that, So with this, we'll be able to show that the F2 seminorm, the 2 seminorm of F2 tilde is positive, okay? Because first of all, since lambda n prime has positive lower density, I can go along it and still have, and it's a subset, it's a sequence of subsets of lambda n, I can still have positive correlation, but now I only depend on capital N prime. So now what we're going to do is we're going to forget about this. So remember, we had two things, right? 11 and 12. Now we're going to completely forget about 12. And just from 11, we're going to be able to say that, that the 2 seminorm of F2 tilde is positive. And so this strongly relies on the fact that the chi n ones only depend on capital N. So here's how we do this. We start with this, which we know is true. We precompose everything with Tn1 prime, so here and here. And then we apply Cauchy-Schwarz. So what we get is from the Tn1 prime here pops this eigenvalue. And then just applying the definition of delta n1, we get this. Okay. And now after Cauchy-Schwarz, we get this square. And so this average here comes from the fact that applying the Tn1 prime, we get this, everything is T invariant, right? So I can apply it as many times as I want and even take an average. I'm not going to change the value, right? Because the integral is T invariant. So I can take an average and I can do this with Cauchy-Schwarz. And here, the next step is just, instead of going along lambda n prime, now I want to forget about the lambda n prime. And I can indeed do this because it has positive lower density. So if I want to show that this has this limit more particularly is positive, because this one is, and this the sequence of lambda n primes has positive lower density, it's enough. Okay. So now, what I want to do here, I didn't write this explicitly, but I want to use the Van der Kolk trick, but only applied to this average here that is a finite average, right? And then precompose it with t to the minus n1 prime to deduce this. Okay, so here I'm skipping some steps, of course, but the main idea is when we're at this point, notice that, so this guy here, the two averages with N1 and N2 give you the 2 seminorm of F2 tilde, and this is positive. But we have this guy here that's bothering us, right? This should not be here if I want to conclude the proof already. So it takes another technical step that I'm going to skip to show that we can actually get rid of this and just have the 2 seminorm. So here, actually, you can, working with this definition over here, you can see what I said before about if you have something in the Kronecker factor, then the 2 seminorm is the same as the L4 seminorm of, what do we want? Okay, so maybe to be more precise, if you have F is the sum of Cj chi j, where chi j are eigenfunctions, then the 2 seminorm of that is equal to the sum of the absolute values of the Cj to the 4th power. So you can use this formula to check this. You will see that a bunch of things cancel when F2 is an eigenfunction. Okay, so this is some previous comment I made. So, but I also want to point out to you that the fact that we can get rid of this is because here we only really depend on capital N and the second variable N2. So this is a crucial fact. And this comes from our previous analysis of all of this, the eigenfunctions only depend on N and blah, blah, blah. Okay, so yeah, so this, okay, I'm cheating, of course, a little bit. With some finer analysis, I promise you that you can show now that the 2 seminorm is positive. And this is really all you need, right? So you've finally been able to say that the 3 seminorm being positive implies that the 2 seminorm is positive. And that's a huge step. And now what I'm going to show you is that with this, we're practically done without too much work. Okay, so final step. Now I want to reduce, first I want to reduce to the case where the system is ergodic. And of course, we want to use the spectral, sorry, what am I saying? The ergodic decomposition to show this. And here we rely on the following fact, that is, if my ergodic decomposition is mu is equal to the integral of measures, then having trivial rational Kronecker projection is the same as having it for the ergodic measures almost everywhere. And the reason for that is that you can, so to show this is the same as showing that the spectral measure associated to F. So if you look at the correlation functions F, T, and F, and you use Hertlotz's theorem, you want to show that these measures don't have any atoms at the rational points. But then you can use the ergodic decomposition there, because having no atoms for mu is the same as the mu t's having no atoms there as well. Here we're crucially using the fact that Q is countable to be able to say this, right? Because we're taking a countable union of 0 measure sets. Okay, so this is the first reduction. My system is ergodic without loss of generality. Now, the first step will be to show that if F1 has trivial rational Kronecker projection, then we converge to 0, right? So that's one of the things that we want to show. But okay, so we go by contradiction. So suppose that it's not true, then we know that F2 tilde in the 2 seminorm is bigger than 0. So recall that by what we said before, that means that F2 tilde must have some positive correlation with an eigenfunction. So there exists some eigenfunction of eigenvalue 1 such that this is non-zero. And this, recall that this guy here is appearing because this is a definition of F2 tilde. Okay. Now, let alpha be the eigenvalue of this chi. So now what I want to do is just precompose with t minus n squared. And I get, of course, the e to the n squared alpha. And then the only other thing that survives in terms of n is tn f1 bar. But if this integral is not 0, what this means is that these averages do not converge to zero in the L2 sense, right? Because they are correlating with the GKs, right? And notice that then you don't really depend on, you don't have to care about the GKs, because all I'm saying is that the averages must correlate with something. But now here, again, I can use the spectral theorem to say that, well, if this does not converge to zero, how could this be? This could only be if T is rational here, right? This is what we said before. So with the spectral theorem, I transform star into this not converging to zero, but n squared alpha plus nt is always equidistributed if T is irrational. And moreover, there should be an average here. I just realized I forgot it. Okay, so pretend that there's an expectation here. But notice that from this spectral measure that we're implicitly saying here, there's an L2 of some sigma. It's coming from F1. But what did we assume about F1? We assumed that it had rational, trivial rational Kronecker projection. So what that means is that if T is rational, the measure has no atoms there, so it's zero. So that means that in the L2 sense, this just converges to zero. So in fact, what follows from this is that this average converges to zero in the L2 sense. So that's a contradiction. Okay, so what are we doing here? Notice that we're reducing to this, and the fact that F1 has trivial rational Kronecker projection implies that the averages must go to zero. So we get a contradiction. Okay, so that's the first step. Now that we have the first step, we want to show the second step. So if F2 has trivial rational Kronecker projection, then we want to show that the TNF Tn squared, TNF1 Tn squared F2 goes to zero. Now, what did we show in the first part? We said, sorry, I'm pointing with my finger, but this is useless. So we showed that if F1 has trivial rational Kronecker projection, then we go to zero. So we might as well assume, by subtracting if necessary, that F1 is actually measurable with respect to the rational Kronecker. So if we further expand, we might as well assume that T and F is just e to the n alpha for some rational alpha. Okay. So this is just an approximation argument. Namely, we may as well assume that F1 is measurable with respect to the rational Kronecker, and the rational Kronecker, the functions that are measurable with respect to that, can be approximated by finite linear combinations of eigenfunctions. So if we just move the eigenfunction outside, because the T stops affecting it, all we're left with is the eigenvalue here. And of course, because this is the rational Kronecker, alpha must be in Q. And now, just to finish, we can use the same argument as before. It's just that here there's an n squared. But at the end of the day, what we do is we have to look at these averages, right? And we have to analyze when they don't converge to zero. So we know they converge to zero when T is irrational, but when T is rational, we're now analyzing the F2. And by assumption, F2 has no rational atoms. So for all intents and purposes, these averages converge to zero everywhere. So these averages converge to zero in the L2 sense. And that's it. So that finishes the proof. Okay, so let me stop here, and you can go ahead and ask any questions that you may have. So I realize that step number 4 is very complicated. I just wanted to give some of the main ideas. Okay, so it's perfectly fine if you couldn't follow everything. So I guess the main ideas that I want you to remember are showing that the eigenfunctions only depend on n, and because of that, and some finer analysis of the averages, we were able to show that the 2-7 norm is 0. Okay, so that's the main thing I want you to remember from this. All right, so any questions?
Yeah, so I have a question. So, I mean, I'm I didn't follow all the details, but I think you did a good job of conveying the general sense of how you do this sort of semi-norm reduction. I guess I'm curious how this extends. Right, I think you said like the general framework is you can get controlled by semi-norms, then you just reduce one step at a time.
Yeah.
And it seems like reducing to Kronecker maybe isn't how the general case can go, because you're using spectral theorem and Kronecker factor. Like,
yeah,
it seems nicer with spectral theorem than going to the other steps. So is there, can you give some sense of how?
Yeah. That is a very good point. So notice that here we were kind of hampered by the following fact. So let me just look at the theorem. If I can find it here. Wait. Oh no, sorry. Here. Okay. So look at this, right? Remember that like part of the argument was what happens when we look at e to the mt1 plus m squared t2, right? The problem that we have here, as opposed to say if these were Hardy field functions, is that for given t1 and t2, we may not converge to 0, right? So there are some problems for particular rational values of the eigenfunctions, right? So what that implies for us is that the analysis of being able to reduce the semi-norm is much more complicated. And notice something very interesting here, that is that we're only able to reduce it to the Kronecker. We cannot go all the way and say, well, the integral must not be 0, right? Because recall that the original problem here was, well, when do we converge to the product of integrals here, right? So ideally, we want to say, by reducing all the way to the lowest semi-norm possible, we want to say that this does not converge to 0 if the integral is not 0. So what follows from that is that I can just subtract the integral, right? And then reduce it one more step. So the difference between the example that I showed and the general case of equidistribution, if and only if we have semi-norm estimates and we have equidistribution, lies exactly with the fact that let me see if I can find them. These kind of estimates are very good for what we call jointly ergodic sequences. But for polynomials, these are not so good, right? Because we have to very carefully analyze what's happening with the rational eigenvalues. But for general sequences that are very well distributed, here we have a much easier time, and we can actually go all the way down, not just to the Kronecker, but to the integral, because we have these good estimates. And notice that we don't have these estimates for, in the case that this is n and the second one is n squared. So instead, we kind of have to make do with, well, if we really carefully analyze these estimates, they actually don't converge to 0 unless the eigenvalues come from a finite set. And because of that, and even more careful analysis, we're able to complete the proof, right? Because here I'm skipping steps. So that the steps that I'm skipping are related to exactly this issue. So in a way, I want to say that the general proof, once you see how this one works, is easier because you don't have the trouble of having to distinguish between different types of spectrum. So in the general case, since you have very good equidistribution results, you can actually more easily reduce the semi-norms one by one all the way down. But in the case of polynomials, you cannot do that. And you have to, so here, for example, so notice that in the key step, right, when I reduced the, here, when I reduced from 3 to 2, I had to use at some point the non-trivial Weil estimates, right? This was necessary to get a finite subset and so on and so forth. And this is what allowed me to say later on here, right, that I can conveniently get rid of this guy. So in the general case, you're able to get rid of this guy because a similar term appears, right? But you can do this way more easily because you don't need these finer estimates to be able to show non-dependence on capital N, right? So the fact that you have better estimates in the exponential sums allow for some of the steps that here were kind of hard to go more smoothly. So I would say that that's the main difference. I realize I gave kind of a long answer, but I hope I was able to convey some of the differences at least.
This might not be related to your talk, but I'm always wondering about it since so much of these problems that we study in ergodic theory boil down to having something to do with the Kronecker factor. So we know if you want an average of eigenfunctions to be 0, you don't need to divide by n. In fact, you could divide by any function that increases at all, right? Because it's going to be a bounded sum. And then using this knowledge, you can show that if you average eigenfunctions along squares, then you only need to divide by, I'm tempted to say square root n, but just to be safe, I'm going to say n to the power of 3/4.
Right.
And if you average like Tn cubed of eigenfunctions, you only need to divide by n to the 7/8 in order for the average to be 0. So because this is so intimately related with the Kronecker factor, and we're just working with basic polynomials n comma n squared, is there any chance you could divide by something smaller than n and still, I don't know, get the correct limit? Or if you take out the constant term, I guess you would have to take out the constant term for this to have any chance. Take out the constant term and have it average out to 0.
So what I'm thinking here is that part of the analysis of making all of this work relies on you being able to reduce the seminorms. And the seminorms are defined for 1 over n, not for 1 over n to the 3/4 or something. So maybe that's the only obstacle I can think of right now, because so all these reductions that we're saying, right? So when we're saying here, so at the end, right, we're saying if this is 0, then the averages go to 0. We do need the averages to be with 1 over n, because at many points in the proof, we're doing some reductions, and these reductions rely on seminorm estimates, right? And in order to construct the seminorms, I believe you actually do need the averages, because you need to converge to the invariant factor, right? So you need the 1 over n sum from 1 to n. Maybe, so one of the things where I think this could, this whole paper could be enhanced is by, instead of taking normal averages, you can take W averages, right? Which is what Joel and Florian and Bergelsen do in one of their one of their papers, right? They look at, instead of actual equidistribution, they look at weighted equidistribution. So something like that, I think, could be done here, because there are still several sequences that are well distributed along some weights, and I think that the averaging scheme of weights still kind of converge to something invariant. So from my point of view, all you need to make sure is that the averaging scheme that you choose is such that if you just apply it to T and F, it should converge to the integral of F in the case where the system is ergodic. So so in a way, I think that this could be enhanced, all the results in the paper and so on. But I'm not sure how you would do it for what you have in mind, because what you have in mind is a drastic improvement from an averaging scheme to I don't know. I think that the weights don't make sure that you converge to the integral for the ergodic case, right? So then yeah. Sorry for not
But
being able to say.
wait, you did mention something. You said you would need your averaging scheme to converge to the correct value when the system is ergodic.
Mm. So for example, you would need 1 over n to the 3/4 sum from 1 to n t and f to converge to the integral of f. And I'm not sure that that's true generally.
Well, that's not going to be true if you just take the constant function, but it will be true if you take non-constant eigenfunctions. And then that naturally leads to the question, what happens if you take a weakly mixing function? So do we know of weak mixing functions where the average is actually little o of n? Like, are there weakly mixing functions where you really need to divide by n in order for the average to be 0? Or is weak mixing strong enough to maybe let you get away with something better?
There was a paper from last year. I have to check it though because I don't remember exactly what it was saying. But the author was able to save power, and it's very similar to what you are asking, Sohel. Now, for what Andreu did, I'm a little bit skeptical at each point that he's using Cauchy Schwarz, because when you're using Cauchy Schwarz, then one of your terms you're using that it's bounded. So even though if you start with n to the 3/4, then at some point you will have to subtract the 1/2, exactly because you're going to have the term which is with the constants, and you're going to have n to the 1/2. So in order for you to have the simplification there, what it will remain in your sum, it's going to be for sure something of power less than a half if you start with something less than 1 initially. So I'm very skeptical on any point that Andreu used Cauchy Schwarz that you can get something more. But I can search the paper that I said that there is some saving in dimension, and I can share it with the rest of you. But I really don't remember what were the assumptions. I just know that it's something like mean ergodic theorem something. So I will just have to search the files, the archive files that I keep.
Okay. Yeah, I would be curious. I am curious. I want to see what they did.
And it's very interesting what you're asking, because there are very few results that that we know that you can do something similar. I mean, a few weeks ago, it's an old paper of Bourgain, but I checked, for example, that they found, I don't remember the author of him, but they find some particular combinatorial expressions. At some point, maybe I can talk about this, or maybe in the future, some of the participants can do that. And the important thing is that exactly what you said, that they are trying to see if you need to divide with n, or you divide with some power of n less than 1, and that's very important and rare. So maybe there is a connection to what you just said. Who knows?
Yeah,
so, yeah.
I remember now the reason I got confused between square root n and n to the 3/4. So, number theorists also use the van der Korpit trick. And I saw a book about van der Korpit trick where they have a variant of the van der Korpit trick for when you're dividing by something smaller than n, like if you're dividing by n to the p. And if all you do is naively use this variant of the van der Korpit trick, you can show that the averages with tn squared, if you divide by n to the 3/4, are gonna end up being 0. But I believe it's a relatively important theorem in number theory that the averages of e to the 2 pi I n squared alpha is big O of square root n, not just n to the 3/4. So I know that you can prove this result if you use something more than just a variant of van der Korpit's theorem. And maybe I should know the name of this result because I think it was relatively important. But for now, I just remember that it's a result.
And how do they deal with these things? Because you just said that it's not just this van der Korpit. So are they doing any estimates of exponential sums? I guess. What else can they do? So do you remember the proof of why this thing is big O of the square root of n?
I didn't even try to read the proof.
Okay.
I have a source for the proof if you want to see it, but I was basically trying to see if this van der Korpit variant could do anything interesting, but apparently whatever it could do was already improved upon by someone else in this context of exponential sums.
Yeah. So, I have no knowledge of these techniques at all. And it's just curious to me whenever we can have something like this with smaller dimension, let's say. But also it's the nature of what we're studying usually, that you exactly because you care about the upper density, you just divide everything with n. So, but it would be very, very interesting if you could say something more, or some of you could study something like this, definitely. And yes, your question makes total sense. Very nice question, actually.
Yeah, like I'm also wondering maybe if the transformation is more than weak mixing. If you have a Bernoulli transformation, can you say something? Because if you take n independent functions, then their average, you only need to divide by square root n to get the correct value. And Bernoulli is, I guess, close to independent. At least there are some independent generators, but I don't know what happens when you start taking linear combinations of them. Maybe the square root n will not be good enough, but then you can maybe get square root n plus epsilon or something. So I don't know. This is something I also have not seen much written about in the context of ergodic theory, but I was just curious. Shows up in GPSS once in a while.
So do you want to stop recording in order to discuss for the seminar for next week?
Sounds good.